So this example is aiming on performing the 2D analysis of the construction of the spread concrete lining tunnel. The SCL method is a soft ground applications. So it's by using the new Austrian tunneling method. So support is provided as soon as possible by the application of spread concrete, which is the shotcrete. So the objective is to model the construction of a SCL tunnel using the convergence combined method to consider the 3D arching effect in 2D model. So this is the some of the information about the material and properties. In this example, we will use the 3 different soil layers, the top layer and siltstone and sandstone, which the material will be used by all the general Mo-Coulomb models. So maybe you are familiar with this, the common general Mo-Coulomb model, so which requires some input parameters such as the elastic modulus and Poisson ratio, and also the unit weight of each soils and the KNF values, and it is the additional required to define the elastic plastic behavior, such as the by defining the cohesion friction angle and the dilatation angle and the tensile strength is required. And about the structure part for the lining, so we'll use the simple elastic material model with the sum of the elastic modulus again. And this is the beam type of element which have its sections. Actually, in this 2D case, we will consider the thickness of the lining with the 20 centimeters. So let me start by using the some of the start file in the software. So firstly, let me open the start file in which the materials and properties have already been predefined. So on the machine main menu, here is the material. So as you can see, there is the different soil material properties with the Mo-Coulomb models. So actually, this is the value which I mentioned in the previous slide, and the siltstone, and also sandstone, the bottom soil layer. And the last one is the lining structure materials. So as you can see, elastic modulus has been defined. And in the section properties, so here is the lining with the beam type element. So in GTS NX, we have this library for the section template. So once you select the section of the structure, then simply you can define the dimension of each size, and then section property will be calculated automatically. So you don't need to worry about to calculate this sectional property by yourself. So firstly, let's create a tunnel section. So under geometry menu here, and the first category is the point and curve. Here we have the different type of the geometry create functions. So this one is the tunnel section creations. About these features, so let me introduce simply first. So these tunnel section modeling features is very useful functions in case of you don't have any section drawings by using the CAD file. Of course, in GTS NX we have the function import the CAD DXF or DWG format if we have these sections of tunnels, but If you don't have this section of the geometry, then you can directly use the geometry creation functions. So among these, we provide the tunnel section modeling. So as you can see in this slide, it consists of the tunnel types, so which it covered the 4 different type of tunnels. So first one is the 3 center circles. This is the most simple one. As you can see, you can define the 2 different radius and angles. And the next one is the 3 center circle with the invert. So you can create a tunnel using 3 different arcs and an invert. The next one is the 5 center circles. It is more the complicated geometries because it requires to input the 3 different radius and angles, as you can see. And the last one is the 5 center circle with an invert. And additionally, in this tunnel section modeling functions, you can also include the rock bolt reinforcement if you have in this section. But in this example, we only consider the lining segment without the rock bolt. And next is you can select the location of these tunnel creations. So here, so we have this tunnel type. So let's select the second one, 3 center circle with invert. And I will use these default values, the radius and angles, and without rock bolt. And this center of this section is I will use the origin. So by using the preview, then you will see that the section will be generated, and then let's click OK. So next step is let's create a line to separate the top heading of excavations from the invert. So in order to consider the different stage excavation for the upper part and the lower part, we need the additional line like this. So for this, again on the geometry menu, here is the line functions. So let me click first the start location at the middle of bottom left here, and click it, and then next click is will be the end location at the middle of the bottom right tunnel sections. So simply you can generate this horizontal line to divide the upper part and the lower part of tunnel excavation. So next, let's create the model boundary of tunnels. The stress arching that occurs around the tunnel is related to its depth, and accordingly, the dimension of the mesh area should typically extend to a depth of around, for example, 5D. Here is D is the diameter of tunnel, for example, and beneath the tunnel invert, and should include the entire height of soil above the ground. Laterally, the dimension of the mesh area should be extended to about 6D from the tunnel axis as illustrated in the figure below. Obviously, these dimensions only represent a guideline, and the engineer must always seek a compromise between reliable predictions in terms of stress-strain distribution and cost. So next step is again, let's define the model boundaries and the soil layers. In this example, again, it consists of 3 different soil layers. So firstly, let's create the boundaries by using the rectangle functions here on the, again, geometry, and the first category, point and curve. So firstly, you can input the one corner, and by using the first method, next input will be the so let's input the first corner coordinate, and the next one is the input the diagonally opposite corner by using the length and height. So here the dimension with the 100-meter width and the 7-meter height. So as you can see, I have created the rectangle to for the model boundaries. And the next step, let's create the additional horizontal line for the soil layers. So first line is so -50, no, -20, and enter. Then you can input the second locations, which is the end location in this line geometry. And then so now I have create the two horizontal lines to divide the soil layers. And let's forward the next step. Next step, we need to create a surface for the model boundaries by using the geometry line rectangle, which was generated in the previous step, and divide the surface by tunnel sections and the soil layers to separate the different soil layers as well as the tunnel sections, tunnel excavations. So here, again on the geometry, and in this case, the second category, we have the surface and solid geometry, and here is the make phase. Now on the phase tab, so please select the boundary 4 lines, and then you can create the surface, which is the one surface. And the next, let's divide this surface by considering the soil layers as well as tunnel sections. So for this, we can use the geometry divide surface. So by using this function on the curve tab, you can select the surface and then select the lines to divide this surface for the tool, and then please select the projection by using the second method, 2-point vectors, and then the surface has been divided. So in order to check the more clearly, let me change the color for each surface. For that, in the last main menu on the tools, here on the geometry, here is the random color. So as you can see here, from the one surface, we have divided the several surfaces to simulate the 3 different soil layers and the tunnel section excavations. And the next step is, this is the end of the geometry creations. From now on, we will proceed the mesh generation. Before the mesh creation, so let me specify the size of the element for the tunnel and soil layers in advance. So under the meshing, and here is the second category part, control, and here is the size control. Of course, during the mesh generation, you can define the size of each element by yourself, but in order to control the size in detail, it is recommended to use this size control for the mesh generation. So here, so let's hide some of the geometric curve in the worktree. So in the model tab, so on the geometry, so please hide the curve, only show the surface. And then under edge tab, so let's select only for the tunnel section geometry by using the mouse dragging, and then 14 edges has been selected. And the method, firstly, we'll use the interval length with the 1 meter size. So since the tunnel excavation, after analysis, we have to check the result especially in this area. So it is better to use the small size of element based on the numerical analysis theory, as you know. So it depends on the geometry complications by defining this size. And then click apply. So maybe you can see that some of the red dot will be seen. So this dot will be used for the node locations, positions after mesh generations. Then next, I will control the size on this part. So please select this horizontal line with the control key by intersecting. And then as a result, two lines has been selected because one is for the upper surface and another one is for the lower surface. So two line has been selected, and then method, I will change the linear grading length, and then you will see that the arrow image in this line. So by using the symmetric seeding, you can define the start length. Start length is in this case on the right hand side. So 5 meter at the boundary, and end length is the 2 meter I will use. So by using the preview button, then you will see that in the center part, the size 2 meter will be assigned, and the boundary part, the 5 meter size will be assigned. Since I use the symmetric seeding options, then you can define this linear grading length by defining the two sides for the start and end. And then click OK. Next, let me predefine the soil properties before the mesh generation. So since we already defined the material property, so on the meshing control and the property control here. So second page step, and select the first surface for the top layer. So you can choose the ID1 top layer and click apply. So similarly, in the second soil layers for silt stones, you can select the surface and then click. Then last one is the bottom sandstones, and then click OK. So we have finishes until these steps. So next step is to generate the meshing for the soil layers first. So on the meshing again, here is the generate and the 2D features functions. So depends on the geometric conditions. You can use the auto pace functions and the auto area functions if you have only the geometry line without surface, and the map pace and map area. In this case, since we already create the surface, then I will use the auto pace functions tab, and by clicking the advanced option, then you can also select the more advanced mesh algorithm for the 2D mesh generations. In GTS NX, in case of 2D plane meshes, you can use the triangle shape or quadrilateral and combined one. So depends on the case and geometry, you can select a different mesh algorithm. So in this example, I use the default option with the linear measure with the element shape, combined triangle and the quadrilateral. The only thing is that let me select the register each mesh set independently options. After meshing, so we have the 5 different surfaces. Then by using this option, then 5 different mesh set will be created on the workstream. So check on this option, register each mesh independently, and click OK. And then select all surface. You can select the all geometry by using this select all icon. And the size, let's use the 5 meter. In this case, since we already predefined the size in the particular geometry lines, especially in the tunnel and the second soil layer lines, this size 5 meter will be assigned only this boundary edges and the top and the second first soil layer lines. So then click OK. So as you can see, the mesh has been generated automatically. So, and since I have used the option checked the register each mesh set independently, as I mentioned that 5 different mesh set has been generated. So the mesh set has been separated because we have to define the construction stages for the tunnel excavation. So now we have the 5 different mesh set for the plane surface. Next step is for generating the lining meshes. So again, on the main menu meshing, here is the generate, and please select the 1D. And then hide all this mesh set, and please show only the geometry surface. For this, only show the tunnel section. So please hide the soil layers and show only the tunnel sections. And select, firstly select the upper part lining. Here we have the 1, 2, 3 lines, and then size. It doesn't matter if we skip this step because we already predefined this size in the size control, but please for sure that size, I will use the value 1 meter, and the properties lining, and the mesh set name this is for the upper lining, and click apply. So similarly, please select the lower part lining, and create the lining as well. So now you will see the lining only here. And for your tip, since we have defined the thickness for this lining section, so under the works tree property, and by using this hidden function, then you can display the section of lining with the thickness. This is only for the display, and for the calculation, again, the software program will use the section property for the calculation of the member parts of the structure part. So let me continue. And for this, now we have the several different mesh set, but most of them there is no exact name. So I will change the name first. So firstly, this by using F2 key and select the F2 key, so you can rename the name for each mesh set. So this one is for the upper excavation, and this one is top layer. The next one is the lower excavation. Next is the bottom is sandstone. Is the second is siltstone. Next step, let me check some point whether the property has been assigned correctly before the analysis. So now this color for each mesh is just the mesh set color. Actually, this is no meaning for this color, but please keep in mind that you have to check the property material has been assigned correctly for each mesh set. So for this, on the toolbar here, we have the display mode, and then you can select here the property color. So for this property color, you can compare this on the worktree. Here is property and 2D. Now you can see that the color in this top layer, the green one, and the second one is the yellow, and the last one is the white gray. So now we see that the property has been assigned correctly for each mesh set. In the previous step, I have used the property control by defining the each soil layers with the correct material before the mesh generation. So again, let me change the mesh set color. And the next step, let's define the load and boundary conditions. In this simple example, we don't have any surcharge. For this function, we already learned about in the previous course. So in this example, I will use only the self-weight and the general boundary conditions. So firstly, let's define the boundary conditions. So here on the static slope analysis main menu and the boundary category, here is the constraint. So in the first and second tab is to define the specific boundary conditions. And the last one is to define the general boundary condition for the model. So just select the last tab and then with the name ground fixity, and then click OK. Then the boundary condition will be created automatically by considering the model boundary. So as you can see on the side boundary, the roller condition will be assigned, and the bottom boundary, the fixed boundary condition will be assigned automatically. And the self weight here. So the load set name is self weight. And as you can see, the component, the y direction is with the value -1. So by default, when you start the 2D project, and then the y direction will be used the gravity direction by default. So accordingly, in the self weight, also the GY will be used the value -1 by default. So this value, as you know, that will be multiplied with the unit weight for each materials for the calculation of the kind of the vertical stress. So again, so self weight, and then click OK, and then the label for the self weight will be seen like this. Okay, so let's forward the next. So now we'll generate the construction sequence. So in the tunnel modeling, the crown or top heading is the upper part of tunnel section constructed during the excavation process with Natum type of tunnel, which is commonly supported by shotcrete lining in this case. And the stability of the tunnel crown depends on the geometrical setup of the tunnel, such as vertical depth, height, and the width of the tunnel, and the material properties of the shotcrete lining and the medium. Assuring the stability of crown is essential for the safety of the tunnel structure as well as the structures nearby if required. So in this 2D modeling, we have to consider this 3-dimensional arching effect. So stage construction analysis is required that the tunnel lining is activated and the soil mesh set inside the tunnel are deactivated. The tunnel 3-dimensional arching impact is simulated by using the lambda or convergence confinement method, in which the proportion of unloading before lining construction is prescribed. So the volume loss is a predicted value. An initial force vector is applied at the nose on the tunnel boundary. Actually, the lambda is initially equal to 0 and is then progressively increased to value 1 to simulate model the excavation process. At some specific prescribed value lambda d, the lining is installed, at which point the stress reduction at the boundary is lambda d multiplied sigma 0. So the remainder of the stress reduction is applied to create the lining stress. So the stress reduction with the lining in place is then 1 minus lambda d multiplied sigma 0 in the intermediate stage sequence. So now let's create the construction sequence. So here on the main menu, static analysis, construction stage, and let's click the stage set. So, and we provide the different type of stage analysis. So in this example, we use the simple static analysis and click add and double click the created stage analysis case. So here we have the construction stage definition dialog box, and in this, firstly, you can input each stage name, and then by using the mouse drag and drop, for example, to simulate the initial phase without the excavation, we have only the 3 different soil layers without the lining. And then, it is useful to change this show data from all to activate. Then you can see that the defined data at the same time on the model. And please check on this clear displacement to reset the deformation in the only to obtain the initial in situ stress. Then click save. And then in order to create the next stage, please click new button. And then this stage is for the upper excavation. And the mesh set is the upper excavation. Let's drag and drop to the deactivate data in order to excavate it. So in this stage, we have to consider the convergence confinement to simulate the 3-dimensional arching impact. So for this, we have in GTS NX the option load distribution vector. So this is for the factor to apply this load distribution. The first one is for the current stages during the excavation, and the second one is for the next stage for the lining installation. So I use the 60% in this stage for the stress relaxation, and the remaining the 40% will be applied in the next stages during the lining installation. And then click OK. And then please click Save. And in order to create the additional stages, please click New button. And this stage is for the upper lining. Only the lining mesh set has been activated. And then click Save. And click New button for the next stage, which is for the lower excavation. And the lower excavation should be deactivated with the defining of the LDF, load distribution factor. So let's use the same factor. And please keep in mind that the summation of this factor should be value 1. So you can check this sum of the factor should be value 1 and click OK. And click Save. And lastly, the lower lining will be installed. Drag and drop to activate data to add the mesh set lower lining. And then click Save. And close the old dialog box. So now we have defined the construction sequence. So let's see that this stage of excavation, firstly excavate the upper part and install the upper lining, and excavate the lower part and install the lower lining. This is the common page procedure of the tunnel excavation. You know that excavate and install the reinforcement like this. And the next, before learning the calculation, we need to set some of the analysis options. So under analysis here and the analysis case here and general. So as you can see, we can create the several analysis case. For example, if we have the static analysis and dynamic analysis and slope stability, you can create the different type of analysis case if you want. So in this case, we'll only run the construction stage analysis with the SCL tunnel. And then let's select the construction stages. Since the stage of construction has been defined in the previous step, and just to check the analysis control box. And in this analysis control box, you can define the K-naught value, K-naught procedure for the initial calculation of the initial stress of the before the construction. Then click OK. And then let's run the analysis, then perform and click OK. Now it's running. So all the information during the calculation, in the output window will be will show the sum of the procedure of the calculation. So now it has been finished. So the total calculation time is only the 12 seconds in my laptop. Anyway, now let's check some of the results here. So to check the result, you can just simply move to the results tab. So and based on the stage of construction definition, the all result will be categorized the tree structure like this from the first stage and the last stage. So firstly, let me show the last stages, low lining, and the displacement, and the total displacement. So, and if you install the firstly, and then you will see this like the result like this with the initialized functions. So from here, let's control some of the options on the result. Here is we have the category general, and here is the deformed. By default, we use the deformed, and you can change to undeformed here. And you can also change the control plot here on the smooth menu. And some of the functions, so show hide the actual deformation here. For more detailed operation for this post-processing, you can also check at the property window. Under this property window, let's check the deforms, and here is the actual this deformation I have selected. It's the same function, the deform, undeformed, and if you change the factor and click apply, then the actual deformation will be shown. And the next function is regarding to check the result on the model directly. So again, on the main menu result here and the advanced category, we have the proof. So by using this proof, so by clicking this symbol, you can fix the dialog box. We have button maximum and minimum. So simply click this, and then let's change the contour plot from the total deformation to the, for example, vertical displacement. So let's again click the maximum and minimum. So as you can see that the value for the will be maximum and minimum will be occurred on the location of the crown and the bottom center. And additionally, by using the proof, simply you can click the mouse on the model directly. Then you can see that the result tag if you want. So for this, this is the displacement result. So all the result shown from the node location. So like this, just clicking the mouse, then you can display the result tag with the value attached. So it is very beneficial and useful function to display the result. And also by default, we use the unit here on the right bottom, the force, kilonewton per force, and meter per length. So you can change the unit of the length, for example, millimeter, and then the result value will be changed by according to the change of the unit in the model as well. Next, let's check some of the member parts of the lining structure. So here we have the lining with the beam element. So on the beam element force, the first one is axial force. So we can see that the axial force diagram, but for the soil ground area, let's hide by using the function on the result. Here is the general, no result, exclude. So from here, you can show only the diagram plot of the beam lining element, axial force result in this case. and the bending moment. You can double click the bending moment Y. This is the coordinate, local coordinate, element coordinate, bending moment Y. You can check for the moment of the lining structure. This is the end of my presentation training today. During my presentation, some of the question has been written in the question window. So let me cover some of them. As I mentioned, you can write your questions during your homework in the Skype chatting room. We have already shared the link for the Skype chatting room. So first question is from regarding the unit weight of soil. So we have of course, you can define the two different unit weight. So in this general tab, you can define in the first general tab again, you can define the so unsaturated unit weight, and then in the second tab, you can consider the saturated unit weight, because this value will be used for the underground underwater level, and the first value will be used for the over the water level, as you know. And next, so so there are many questions. So one is from the Adi. Please explain more how you include the 3D effect into 2D effect. So as I explained during the presentation, by defining this convergence confinement method in the 2D modeling, you can consider the 3D effect like in the tunnel excavation. So most of the software, numerical software, has this kind of function. So in GTS NX, in order to simulate this effect, again, we have the load distribution factors during the stage of construction define. So again, here on the staged excavation, so this option, we just call the LDF, load distribution factor, in GTS NX to consider the convergence definement method. Some other software, they use another name of this, you know. And another question is so is it possible from the Eva from the Czech, is it possible to use the different modules of elastic corresponding to the loading and unloading? Yes, of course. If you define the separate the elastic modulus for specific soil layers, then over the structures, you can use this to simulate the change of the elastic modulus. In this case, you can use the change parameter. So from under meshing, so under static analysis, here is the boundary. we have the function, the change property. So by using these options, you can change the property for the specific area mesh set, even though you have the another you have defined another material for this mesh set. So during the excavation or during the construction, if you want to consider the change of the elastic modulus, then please predefine the separate material and then use this change material change property. And this is regarded as the boundary condition. So you can assign this boundary condition on the specific stages where you want to consider the change property. Okay, so time already has past the 1 hour. So rest of the question we will provide the reply after this webinar.